Yes, I have started.
Okay. Okay. Uh, Good evening, everyone. Hope you all of you are doing well and getting ready for your AeroTHON competition. But before we get into the agenda of today's webinar, I want you to answer us in chat uh, about this picture that you see on your screen. That which stairs are you going to do? How are you building your UAVs? Let's make it easier for all of us. Let's use the R for red color, yeah, orange for undecided, simulation for green color. Let's make it G and let me know which side you are. Are you directly building your UAVs or you are doing simulations first and then you are making your UAVs work, or still undecided how you guys are doing it? G, okay. Are these saying they are going for simulation first? Good. I'm interested to know why you guys are going for simulation. Why not directly building it? Doesn't simulation require your extra time? Anyone other than Adi? I'm assuming if the most of the people are not answering this, either they are in the undecided or they are on the directly build phase. But if you have any other thought, then let me know that no, we should go for this phase or another phase, or we should have any fourth way. uh, Let me know in chat, because this is going to be an interactive session where from both sides we are going to have multiple questions, which I'm going to answer, and I'll have also some quiz along with the webinar, along with this PDP session workshop, where we are going to learn from each other. You guys can let me know in the chat. Okay. In the meantime, till you let me know in the chat, let's move forward and see what's the today's session. So today we are going to talk about how can we simulate drones with the Simulink. And before even that, we are going to talk about why the simulations are needed. Why should you go for the simulation? Why not directly building UAVs? What are the benefits and what are the pro and cons of both the approaches? Um, Most of you would be knowing me, but if you are not aware, I'm Kushin Lakhara. I work with MathWorks as an education programs aerospace engineer, where I helps the student competition teams like you to adopt industry workflows and accelerate their workflows for UAVs. So our goal for this webinar is going to be that by the end of your webinar, you should be able to simulate your mission and be able to create a foundation for smarter drone algorithms, and uh, also building up the algorithms and deploying them to finally to their hardwares, and achieving the capability test of your vehicle even before your vehicle is built. So this is not going to be the just one session where we are going to discuss this. We are going to have the three sessions to help you build smarter drones with industry workflow. So this is our first session. In the today's session, we are going to discuss flight dynamics and modeling of an aerospace vehicle. Moving forward, we will talk about what is the open loop flight simulation and closed loop flight simulations. We'll also discuss various fidelity level enhancement in vehicle modeling, and finally, we'll talk about how the environment modeling is done and how can we build up the synthetic data generation. So this generated synthetic data can be used for training your neural network model or for your image processing approach. We have the next session where we are going to talk about whatever the algorithms that you develop in the Simulink, how do you generate the code for that and put on your flight computer hardware that can be NVIDIA Jetson or Raspberry Pi? Also, how do you develop your flight controller in Simulink and deploy on the Pixoc autopilots? We are going to talk in detail how these codes are generated, how these codes are deployed, and finally, how do you make the hardware in the loop testing work? In the third session, my colleague Shovik is going to teach us about how can we build the perception-driven smart drone. So, Shovik, if you are on the call, would you like to let us know what are you going to discuss during this session?
Sure. Thanks, Kushin. Am I audible?
Yes, yes, you are
Okay,
audible.
awesome. Yeah, so basically, once you see how to simulate drones with Simulink and then code generation and do hardware deployment, in the third one, we will cover a little more on the perception side. So, if you have a camera on board a drone, how do you take the images? How do you integrate those cameras with the drone? And after we get the images, then we have to do a lot of pre-processing on computer vision techniques to find out, things like segmentation and stuff to do a ground truth labeling, which we call. So once we basically prepare some deep learning algorithm. So once before the algorithm, we need to get the data ready.
Oh
So
yeah,
that's where we'll do the data part, right? In AI, there is always a thing. If you don't have the data, if the data is a garbage, then whatever we get output is also garbage. So
true, true.
so we do that and then see how do you do on deep learning on top of that. That's the whole idea.
Oh, wow. Wow. It sounds like we got a complete pack of sessions for these students to build their smarter drones for the Aerothon. So yeah, in the three sessions, we are going to talk about how do you do flight simulation, how do you develop smart algorithms, and finally, how do you deploy on your vehicle? Because working in the simulation and just in software is not the industry workflow, but bringing these models together and finally deploying it on hardware is the final goal of this. So yeah, this is going to be our three sessions for this goal, and be tuned. You will get the links for the next upcoming session soon through the organizers. So in the today's session, we are going to learn about simulating drones with Simulink, and we are going to start with some introduction to model-based design. What is it about, and why is it important? Moving forward, we'll talk about flight dynamics modeling and simulation. What is the flight dynamics? How is it important? Why should we do it? And what are the various ways of it? Moving forward, we'll also talk about multi-body drone simulations, where if your vehicle has to drop a particular object to a target location, or if you have anything where the multiple bodies are involved. So how do you bring various your CAD geometries within the Simulink environment and perform the simulation? And finally, we are going to talk about what all the resources we got for the AeroTHON teams and how the AeroTHON teams can make the best use of all of these learning resources. So let's start with the first session. But before I go to the model-based design, I would like to ask audience, what is your motivation to learn about simulation? What do you think? Why the simulation is important for you? I see lot of students are there. I see the someone named challenges. I'm believing this is a team name challenges. Then I have UIET fire files. Charita, anyone who wants to take wild guesses on this? Let's make it an interactive session. Please feel free to post all of your questions in the chat. We'll try to answer along with the session and also at the end of the session. So Aryan is saying we need to see how US unmanned aerial system might perform in the actual competition. Uh, that's really good. You want to test your capabilities, but simulation is much more than that. Uh, think more from the perspective of when you are designing it, what it can help you to assess. What if US or UAV or drone is not performing well and you build it, then are you going to rebuild it? Are you going to invest more resources? These resources can not be only in the form of money, but it can be in the form of time, your manpower, your working hours, managing your academics, all of them. So let's see how does the industry do it, but more from an Aerothon perspective. So if we talk about the workflow for Aerothon, how do the teams design their rotorcrafts? They do the research on the based on the what are the existing technologies are available and what are the previous year configurations are there. Accordingly, they would do the component sizing, material selection, performance analysis. They will select their mechanism to drop the payload or pick the payload. Once that's done, they go for the UAV manufacturing and they do the manual flight testing. Flight testing tells a lot about the flight performance because that's what you are going to perform in the actual competition. And moving forward, they to make it smart or to make it autonomous, they work on guidance, navigation, and control algorithms. So they would work on these algorithms, and finally they integrate with hardware, which makes these autonomous which makes them ready for the autonomous flight testing. So this workflow, if we compare to what is used in the industry, this is similar to the traditional design workflow, where first a vehicle is designed, then their the algorithms are developed and implemented, and finally they are integrated with the hardware. So now if we let's look at closely and understand what can be the problems with the traditional design workflow. So we have seen the workflow. One thing I see is there is no feedback in this process, and if we don't have the feedback, we will not be able to improve our design. So think about you are at integration stage and you found some error which is coming from your requirements change or which may be coming from any other change in design, and now it has affected your complete design cycle. So how are you going to handle it? So yeah, that comes with another quiz for you guys. What do you think? What are the problems with the traditional design workflow? Starting from the Aryan saying it may be time consuming and repetitive. Very true, Aryan. So let's explore these problems one by one, starting from the requirements. Uh, Requirements are in the documents or this written somewhere. So if your requirements are changing, you are not able to make the immediate change in complete design. That means you don't know if your requirement A is changing, which component B, C, or D you need to change in your rotorcraft. That's the one of the biggest problem. Uh, it involves the physical prototyping. Physical prototypings are obviously expensive, prevents rapid iteration, no system level testing. These are some of the big problems and which actually makes the complete engineering design cycle costly. Moving forward, it's a manual coding, time consuming. Its manual coding is obviously time consuming, and because it involves humans, you can always introduce defects and variants, and if some other team members are using it, then it's difficult to reuse. Moving forward, they go for the traditional testing. So design and integration issues are found very late. Now, if you have any issues in the requirements, you have to go back to the requirements and then you have to restart the complete phase. But you are not able to understand that making the change in the requirement is going to impact which subsystems or which components. So this brings to the traceability issue. So what's the solution? Solution is the model-based design workflow, what industry prefers, and most of the aerospace companies across the globe prefer this workflow. So they put the requirements into the models. These are simulation models. Instead of writing them in a Word document and then making the changes in the design. These are they mention the requirements in the models, because these designs are the multi-domain designs, and you can do the multiple simulations. So always the requirements is directly affecting your designs, and you are able to see that how the requirements are related to your design configuration. Moving forward, for implementation, no more manual code writing, but you generate the code from models. You don't write any more code, but you develop the algorithm. And for algorithm, whatever the programming language you need, you generate the codes for them. Either it may be C, C++, or your hardware has specific requirements. You generate the codes, but from the standard templates, which are actually compiled with the industry compliance. And then the main feature is it has continuous test and verification as part of this workflow. So whenever we are making any change, or even we are at the early stage, we are always testing how our model is going to perform and how our model is making effect on the subsystem level and complete system level and assembly level. So that brings up another benefit. And as requirements are into the model and we are testing it continuously, it's bring the traceability to requirements. So no more problems of understanding that what component is making what performance change, or what requirement will affect what components. You have a traceability to requirements. You can always trace the final outputs. It leads to shorter timelines, reduced cost, reduced interfering hazards, and obviously we are engineers. As an engineers, instead of trying to work on small things, we can work on much bigger level. That is, we can work on engineering systems and engineering algorithms. So which are the tools which you can use for model based design? So there are tools, MATLAB and Simulink. So if you guys are new to the MATLAB and Simulink, MATLAB is the language of technical computing used by scientists and engineers across the globe for various purposes: numeric computation, data analytics, visualization, algorithm development, and deployment. And we have the tool, more than 130 toolboxes, starting from audio toolbox to aerospace. So with wide industry applications, we also have the Simulink. Simulink is a platform more for the platform for the model-based design, and this is used by the industry as a block diagram modeling approach for modeling, simulating, and analyzing multi-domain system. And it has the automatic code generation capabilities, which actually saves you from your writing codes. It has huge applications in control systems, signal processing, communication systems, and more. So now, as we have learned about which are the tools uh, we can do, which are the tools for the model-based design, let's move forward and get to the main meat of this webinar of the flight dynamics modeling and simulation. And that's where we are going to do a technical deep dive into the aircraft dynamics of a vehicle, or how an aerospace vehicle actually works. So before we go for that, another quiz. Why do we do the flight dynamics modeling, or something called 6 degree of freedom modeling? Why is it important? Can we do not bring just the various parts into the simulation model and bring them together and see how they are going to impact? Let us know in the quiz. I'm waiting for your answers, guys. We have the limited time. The more we interact, the faster we go, the better questions we have, the better answers I will have, and we are going to have much impactful session. By the end of this session, I want you guys uh, to move away with few learnings that how you can directly use this session for your AeroTHON competition. So Om is telling to get the movement of the bodies in the 6 degrees of freedom. True, you can, Ishant is telling to be able to trace the trajectory of drone. So if you are able to trace the trajectory of drone, you can actually see if your vehicle will be able to complete the mission or not. Ashish is saying since the UAV's whole system like a Rubik's cube, every movement needs to be taken into consideration. Wow, yeah, true. Drone is a free body, unconstrained body, or inertial relative body. Uh, okay, So yeah, it's a free body. So the main idea of doing the flight dynamics modeling is actually to mimic the behavior of the actual vehicle. So you guys must have done the CFD modeling, CFD simulations for your vehicle, or you would have done the thrust motor bench test for your propulsion systems. But where does this final data goes, and how does it help us to actually bring the bring the final results and see that how my actual vehicles are going to behave? So Tejaswari is saying predicting aircraft behavior, that is our final goal. Instead of predicting, Tejaswari, I'll say we are going to estimate the aircraft behavior, and Aryan is saying only accurate way to simulate the complete body. Well enough. I think you guys are smart enough. You don't need this session at all. But still, let's move forward for this session and see what's this. So to understand the 6 degree of freedom modeling, we have to understand about an aerospace vehicle. Uh, if you see an aircraft on the screen, don't worry. I understand that this session is for the rotorcrafts. We'll get into the rotorcraft dynamics, but the main idea is to understand an aerospace vehicle's flight dynamics. We'll bring our learnings from here and we'll implement it on the rotorcrafts as well. So on any aerospace vehicle, there are major four forces are there: lift, drag, thrust, and weight. So lift and drag are aerodynamics forces, weight is a gravitational force, and thrust is a propulsive force. Now, the idea is if we have these forces, three types of forces are implemented on vehicle, how these forces are going to make an impact on the motion of the vehicle. If we are changing the any of the controls, either maybe it's aileron, elevator, or rudder, or if we are changing the speed, how our vehicle will perform. So the idea is to understand this. So let's understand this in this way, that instead of bringing these four forces or three types of forces, we are changing them, we are bringing them together in the a body fixed frame, where the small x, small y, small z are the body fixed frame direction, capital X, capital Y, and capital Z are your forces, and L, M, and N are your moments, various moments about the axis. So now let's understand if we can bring these forces in the form of X, Y, Z, and LMN. The idea is how these forces are connected to the various motions. So for a vehicle, we can bring the motions as a translational motion. So forward velocity, sideward velocity, vertical velocity, UVW. These are your speeds. Then we have the about three axes. We have the various rotations. We said roll, yaw, and pitch, and respectively their rates. So the idea is how do we connect these three forces and three moments to these 9 parameters? And that's the main questions. So any doubts? How, sorry, any idea or any wild guesses? How can we connect these with them? Will not take much time, just a 30-second guess. Whatever you feel. I believe we all have learned about Newton's equations of motion. So do you think this our understanding from equations of motion, if we have a force X, can it develop the speed U? If we have a force Y, can it develop the speed V? Can we connect it somehow? So yeah, so these connecting these all the forces and moments with respective velocities and angular motions is connected by nothing but equations of motion. So there are three translational acceleration equations, three rotational acceleration equations, and three rotational velocity equations. So these 9 equations are called your equations of motions. With these equations of motions, you can actually mimic the behavior of a flight vehicle. It may be a rotorcraft or a fixed wing aircraft or even a spacecraft. If you have the information about if you have these 9 equations and you have the information about various forces these are generated, then we can make it the complete flight dynamics modeling. So before we go forward, let's go back to the previous slides and see which were the main forces that we were seeing. So we had aerodynamic forces, gravitational forces, and propulsive forces. Three type of major forces we have. We'll see that how these forces are actually changed into various motion parameters that we see in these slides. Uh, Sorry, my bad. The forward, 3 translational velocities, 3 rotational displacement, and 3 angular velocities. And using them, we can even make the derivative. So if you have velocity, you can actually calculate what distance we traveled. If you have the rotational displacement, you can actually tell what orientation we have. So let's let's move forward and explore how can we develop it. So are you guys excited to learn the implementation of it? Just let me know yes or no in the chat. Or even if you have any questions about 6-DOF modeling or equations of motions, just let me know in the chat. Guys, if I'm not getting enough yes here, I'm not moving for the demo. We'll only have the theory classes. Do you want the theory classes? Still not enough count to say that we should have the project. Oh, I'm seeing now some good numbers are coming. Good enough. Okay. So with that, let's move to the Simulink and see how can we do it. So this example that we are going to share here is you can access easily. I'll share the link of this in the chat, but let me bring this for you and this for you guys. So if you'll search the, the Flight the Havilland Beaver Unreal Engine visualization. So MATLAB has a large documentation for most of the workflows, and you can use these. You can search about simulating your aircraft, simulating rotorcraft, or whatever terms you have, and you may land to the some of the most relevant documentation. So this is the example we have, and I'm going to copy this command from here and quickly going to my MATLAB, and I'm going to call this example here. So before we get into the simulation, let's talk about few more things. We talked about how what all should a simulation, how the 6 degree of freedom and equation of motion are needed. But in order to create simulation, we need something more. So what are these things? So here we were talking about aircraft dynamics. So in the aircraft dynamics, it includes your various forces and moments along with your 6 degree of freedom equations of motion. Now consider if you have this aircraft dynamics available, we we may be knowing the initial states of our vehicle. How our vehicle at the is it at the ground out ready to take off, or it's already in air? What is its speed? What is its orientation? So if we have this information, and then these all are the information parameters, the states parameters that we consider. If we have the information about states and we are putting some control, so this control is you. In the case of fixed wing aircraft, it may be your engine throttle, control surfaces, deflection. But in case of rotorcraft, it's mostly the throttle of various rotors. So if we have the information about states and controls and we have the aircraft dynamics, we can actually predict the rate of change of state, which is x dot. So if we have the rate of change available and initial states are available, we can integrate and calculate new states. So now if you are implementing these new states, if you are giving the feedback of the new states into the similar aircraft dynamics, you can actually see how your vehicle will behave over the time. And that's the basic philosophy of simulation. Uh, we have these are the basic elements of simulation. But before we move to the simulation of a flight vehicle in the aircraft, I have a question which you can let me know during the chat. Let me know while we go for the demo. Uh, what do you think? What is still missing to make it a realistic simulation? To bring your conditions in which you are going to fly the aircraft, what is missing here? And this is just the basic parameters we got. We got all the X parameters. So just looking at the numbers, will we able to do good with the simulation, or do we need something else? Let me know. What do you think? What can be the additional things we may need here? In the meantime, let me go to the MATLAB and bring other things in the simulation. Okay, so this model, when we will give this command, the simulation model will open. Let me open my simulation model. So this aircraft simulation model is available. So yeah, this is our aircraft dynamics. Let's get into this, what we were discussing on our simulation. So this is our aircraft dynamics model. As we were discussing, we need to calculate first total forces and moments and need to fit through the 6 degree of freedom equation of motion. And through the equation of motion, we will get all the parameters. So we can see here, we are putting all the forces and moments, and what we are getting all the velocities, we are getting the positions, we are getting phi theta psi, which are your orientations, we are getting direction cosine metrics, which are actually useful to change your navigation, change your aircraft's motion from body fixed frame to the inertial frame. Also, we are getting various velocities and angular velocities and acceleration. And these all are fitted outside for the visualization purpose. Main thing here is the total forces and moments. So how do we calculate these total forces and moments? We'll get into that. But before this, this block, 6 degree of freedom, quaternion block that you see here, where it is coming from and what all it holds. So if you get into the block by double clicking on it, you will see that it holds the information that which type of mass it has. Is it as a fixed mass or simple variable or custom variable mass? You can give all these information. It also takes the information of what is your initial position, what is your initial velocity, what is your initial orientation, like phi theta psi, what is your roll pitch and yaw when you are starting, what is your initial mass of your vehicle, what is your inertia, so inertia of your vehicle that it has. So all of this information you need to provide here. Once you provide it, what you are doing is you are actually letting the system know, hey, these are my initial states of my vehicle and these are my initial parameters of a mass and initial parameters, so that system can start the calculation from there and customize your simulation accordingly moving forward. Let's get into this total forces and moments, because it is getting the inputs of total forces and moments. But you would be curious, where do we get this 6DOF simulation, 6DOF block? Any ideas, guys? If anyone is already using Simulink, can you let us know? If I want to, if I delete this and I want to get the Simulink block again, from where will I get? You may be thinking I have messed up the Simulink model. My simulation model has gone. How will it work? I don't have the equations of motion. Do I need to code for it? Some of you are already the Simulink users. I have got this information from your registration data. And also as part of this webinar's prerequisite, we have requested you to go through the MATLAB and Simulink on-ramps. So if you guys have not completed the MATLAB and Simulink on-ramps, kindly complete it to make the best use of the best use of the upcoming session. So let me bring this Simulink block, but if you want the Simulink block, we have the library browser here. So the library browser is collection of various blocks. So consider that the set of codes, set of functions, what we write as a code is actually given a GUI form, and this GUI form is coming in a block format. So if we'll come to the aerospace, come to the library browser, here you will see just here you will see the aerospace block set. So let just allow me to show me to. So I hope now you are able to see the zoomed one and see that in the Simulink we have this aerospace block set. So if you'll go for this aerospace block set, you will see there are various uh, sub menus are there: actuators, aerodynamics, animation, environmental, equations of motion. So I'm more interested in the equations of motion. Let me close few of these. And let me go again here. So you see this 3 degrees of freedom of motion, 6 degrees of freedom of motion, and point mass. So we'll talk about when should you use point mass and when should you use 6 degree of freedom when we are going to discuss about the various fidelity levels. But understand that if your system has only 3 degrees of freedom, or you want to study only few motion parameters, then you can go for the 3 degree of freedom as well. But for the full vehicle study, you should go for the 6 degree of freedom. So this, if you'll go into the 6 degree of freedom, you will see that again there are so many blocks are available: Euler angles, quaternion, ECF, wind, sixth of wind. So all these blocks are available here. It's very easy to bring this block. It's just a drag and drop approach you have to use and place it here. So let me bring it here. Let me bring it here. And now if you'll open, you'll see that all these are initially parameters are 0, 0, but you can change these parameters how this was done for the existing 6-off model. Now in the Simulink, it is quite easy to connect the signals. So Simulink is all about flowing the signals from one parameters to another one, and that's how you can connect your input output from one block to another block. So you're not doing the coding, but you are actually programming in a graphical environment. So let me delete it and let's move forward and see what's we got in the equation, total forces and moments. If we get into the forces and moments, you will see that it is getting 3 inputs. The inputs are pilot, flight parameters, and it has also the inputs from the environmental parameters. So let's talk about first the pilot parameters. So pilot parameters are nothing but the control of your vehicle that you are giving. Then we have the flight parameters depending on what is your angle of attack, what is your side slip angle, how your air is impacting your vehicle. These are coming as flight parameter. And finally, environmental parameters are there, which includes your gravity and density. So these are two major parameters we are getting as inputs. But if you look at this, there are three major types of forces, what we discussed here: aerodynamics forces, engine forces, these are nothing but propulsive forces, and then we have the gravity forces. So if I get into the aerodynamics, you will see, so it has again the aerodynamics equations in detail, which has been bring together and some. So all the aerodynamics coefficients that we get has been calculated: Cx alpha, Cyl, Cy beta. All these are calculated and these are used here as a single value. So you can see that Cx alpha has this specific value of 0.00292. So this value has been given and this value the system is taking, and accordingly it's making all the calculations. So that's how you do your aerodynamics modeling. Similarly, you do the propulsion modeling and gravity modeling. So now aerodynamics and engine forces, which are propulsive forces, are actually contributing to your forces and moments both. But kindly note here, gravity does not contribute to the moments if you are calculating all the moments about your center of gravity. And this one, we are calculating about the center of gravity. So we do not have contribution to the total moment, but we have the contribution to the our system here as the our system here as total forces for the only for the total forces. So that's how we are doing our total forces and moments modeling, and your 6 degree of freedom modeling and aircraft dynamics. I know we have learned a lot of things. Before it gets bored, let me show you, if we run this simulation, how does it look like? So we have something so that we can have something exciting, that why are we learning about it? So let me bring this. Okay, this is my simulated aircraft environment. My aircraft is flying. My hands are free. You can see that no pilot is controlling as of now, and my aircraft is just crashing. Although I have a pilot joystick here using which I can fly, but I'm not using it as of now. And you can see my aircraft has crashed and went into the ground. But this is the photorealistic simulation we have. Let's run it again and see. So we saw that we have an aircraft body which is flying. Then we had the an airport environment where we can see that our aircraft is supposed to land, but it crashes. That's a different thing. But our aircraft is flying over an environment. So this is our 3D scene along with our 3D aircraft body. Now the idea is that how are we going to get this visualization? So are you excited to learn how can you get these visualization and all the parameters from aircraft dynamics? These motion parameters, velocity, your location, position of your vehicle, how are you converting them into visualization? Are you excited to learn about that? Let me know yes or no. Oh, only one. My target is at least 20 years. Then only I'm going to move forward. In the room, we should have enough excitement to do the extra efforts. Tanmay says yes, good. Abhishek, okay, I think we are getting good enough. So let's move forward and come out. So we saw this aircraft dynamics. From aircraft dynamics, we saw that all the states are coming out and which are again fed to the aircraft dynamics. So before we get into what is the pilot and environment model, let's go to get into the visualization. So MATLAB has a very good Unreal Engine based Sim 3D visualization where you can actually customize your scenario and bring your own scene and work on the simulation models. So if you see this here, whatever the positions we are getting, we are just making some changes in these positions, not changing, but we are assigning various body motions to our aircraft's various parts. So here we have a simulation 3D aircraft model. So if we go here, let me just zoom it for you guys. So you can see here that we have a already existing aircraft as Skyhawk aircraft, which is mentioned here. Then we have name of the Simulink vehicle. We have also mentioned initial translational and rotation. You would be thinking, we already mentioned the initial translation and rotation in the 6 degree of freedom block. Why are we doing it? When we are doing it in 6 degree of freedom model, it's more for you are doing flight dynamics calculation. Here, when we are doing, it's more for the visualization purpose. Now we are bringing our vehicle in a 3D environment, a 3D world, where in the 3D world, we should tell, hey, in this world, my GPS coordinates are XYZ or my location is XABC. So that's for this purpose, we are mentioning here initial location, initial translational rotation. You would be thinking that good enough, we do have Skyhawk aircraft. Can we bring our own aircraft? Does anyone have this doubt that can you bring your own aircraft or not? Just let me know in yes or no. You can just type Y or N. That's fine with us. Yes, yes, yes. Okay, good enough. Let's see. So if we have this in the Simulink, okay, we have here, instead of type, we can go for the custom aircraft. And once we go for the custom aircraft, okay, I have selected the airliner, my bad. Let me select the custom and resume it. So once we go for the custom aircraft, it will ask you to for the path of your custom mesh. So once you select the uh, type of type as a custom, it will ask you for your path to custom mesh, and that's where you can bring your own vehicle geometry here. So right now we are taking the example of a fixed wing aircraft, but don't worry, even if you have a rotorcraft, you can bring your own rotorcraft geometry here as a mesh and you can do it. The workflow is very simple. Even if you have the STL geometry of your various parts of your vehicle, we can bring them together and do a multi-body simulation and make it work. That's how you can customize your aircraft for this simulation. You would be curious, like how are we giving the motion of each parameter when I'm giving the control, which would be assigned to what, how is it done? So if you can see here this block simulation 3D Skyhawk pack is actually doing the same thing. It's actually mentioning, should I give it to the propulsion, controls, geospatial gear? So all these motions, all these component assignments also you can do, and you can see their motions. We'll see all these motions in the simulation when I'm going to fly it with my flight controller. The next is simulation 3D scene configuration, and that's the major thing. So you have seen in the simulation that we have a custom airport, we have an airport scene, and that's can see that scene sources are right now default scene is available and airport scene is available. But let's make it, you can bring even your own custom scene. So there are Roadrunner best workflow is there where you can bring your own scenario and do it. Let me bring one scenario and see if that works. So whenever you are seeing in Simulink your model is running and it's taking over time, you can always see its progress here at the bottom. So right now we can see that this showing that it's initializing, and soon we would be able to see how it's progressing forward. So let's see. It's custom made Simulink environment, Sim3D environment, which actually takes time when we first time load it. Let's see if it is right, correct one or not. The environment has started here, but okay. This environment come earlier you were seeing the airport, now you don't see anything. The reason for this is a free environment. It didn't have anything. But using various keyboard controls, I can change all over its motion, and the camera views, all these views are available that you can change. But yeah, you can develop your own custom scenario and do it. Now let's get back to our original scenario and explore further. So now think about a situation of you are having your competition in the November, but before the November, you are building your own Roadrunner scenario here, importing this one in your simulation environment and flying your rotorcraft in that environment. Does it something excites you, or does it something you feel you guys should do it? Let me know yes or no. Ishan says why, yes. Anyone else? Ronak? Oh, good, good, good. So we are going to have few more things, few more demos where you are going to learn about uh, uh, the all these things. But before we get into it, let's get into the work and understand how can we bring it more closer to the our realistic condition. So in the realistic condition, if you see the main parameters are environment. So in environment, we can face that depending on your location, your gravity is changing or your wind conditions are changing. And all these are taken care in the environment model. So as a part of aerospace blockset, you get these gravity models and international atmospheric model blocks that you can use and mention all these information. So if you see this, these 45.5 and 0 are nothing but latitude and longitude of a location, which we are feeding with this, and altitude is continuously fetched from your vehicle states and taken here. So it has a gravity model which takes care of this. Similarly, we have an environmental model. This environmental model is actually calculating your temperature, your speed of sound, your pressure, and density. For this simulation, only density is important. So uh, we are neglecting, we are ignoring other parameters, and we are just using density as main parameter. So you can see that gravity and density are going here. And similarly, we have wind models. So in the wind models, we have the various wind directions and their effects on the angular velocity directions as UG, VG, WG, PG, QG, RG. So this as UVW are your translational velocities, and PQR is your angular velocities of wind. So with these wind models, we actually feed it to the aircraft dynamics. So let's get into the environment bus again. And you can see that when we come into the environment bus, all these parameters are actually contributing for the wind. So you can see that UVW wind, PQR wind, and your vehicle's actual PQR and UVW are getting added. And this brings the effect. So think about if your aircraft is going forward and it's a headwind, then your aircraft will face some more resistance and it may get slower. But if it has a tailwind, which is coming from backward, it may throw your aircraft faster. And so you can bring your environmental effect in the environment in your model. So now, can you tell me a condition, how this environment modeling can be used full for you guys for AeroTHON? Some teams are coming from north, some teams are coming from south. I'm not sure where is it going to be the final? Is it going to be in Bangalore? Is it going to be in Ladakh? Or is it going to be in Kolkata? I'm sitting in my university, I'm sitting in my office, but I'm building a rotorcraft which should be able to perform specifically at particular location where my competition finals are going to be. So do you think that bringing all these environmental conditions here, bringing the right gravitational acceleration parameters, bringing the right wind models that you can face during the competition can help you to optimize your vehicle performance. Let me know in yes or no. Or if you feel there is any other, if you have a doubt, you can also let us know in the chat. I have an exciting thing to show you. How can you make the rains in the simulation? But I'll show you only after you show me, you tell me that does it can it help you for the competition? Yes or no? Or if you think there is a specific condition that can help. Ashish, Tanmay, yes, in making drone more resilient to varied environmental condition. Good enough. Anyone else? The idea of bringing the environmental models here is to make your drone to make your drone to test your drone in the virtual condition which are closer and closer to your real condition that you can feel. And that's how this industry is investing their time and money in the model based design, because even before building their drones or building their aerospace vehicles or even any machines, they can test them into actual condition without costing them money. You saw my aircraft crashed twice, but it didn't cost me anything because it's model based design environment. Let's move forward and see uh, what can we do. So right now I have this pilot model is here. So in the pilot model, we have a pilot joystick block from aerospace block set. You can get this, and using this pilot joystick block, you can connect your RC controller with a USB. So this my USB cable, my RC controller is connected to connected through USB to my system, and I'm going to fly now this vehicle into the simulation. So let's see if I'm a good pilot or not. I don't think so, but let's give it a try. Maybe your pilots can in this simulation uh, your pilots can actually fly your vehicle. So bring to original one. Uh, okay, no. You can see I can make the changes, and okay, I'm not a good pilot. That's for sure. But yeah, think about your pilots is getting trained, or your pilot is testing your drone capabilities performance by connecting your RC controller with your environment. He is doing the same work what you could have tested in the flight condition. But the benefit of these flight simulation is that uh, you will get all the aircraft data here in the Simulink environment. You can actually use it to analyze your vehicle capabilities. If something is getting wrong, if your aircraft is crashing or your rotorcraft is crashing, you can always analyze this data and test your vehicle into the particular condition and find out where is the issue, where is the error. I want to show you the specific capability. Uh, in the AeroTHON last time, I saw that most of the teams got their various data for their simulations, and they did a good work doing their simulation, good work doing training their models. But this came question more from the judges. What if your aircraft is facing the conditions where the visual clarity is not there, or maybe there is a fog, or maybe there's a condition of rain. So how are you going to make the pictures for the how your model is going to take care of this? And here the simulation can actually help you. So if you can see on the my screen, I have this simulation 3D scene configuration block. So here you can see we have weather model where you can actually make the changes in your sun conditions, sun altitude. Similarly, you can go with the clouds, how your clouds are doing it. And then we have this specifically, I want you to check this rain thing. So we are going to this rain density percentage. We are going to shower some rains in our model and see how can how does it look, and can we record these simulations, and can we get some pictures out of it, which we can use it for simulation model. But let's first make these my rain density, say let's say I want some good rain, so let me make it around 20%. We put okay. Uh, so, and let's see how my simulation model performs. I'm not going to fly it again with my RC controller, but do you see some rains are coming? The rain effect has come. So we can increase the rain density. We can make the all these environmental conditions change for visualization. We can place a camera on vehicle and capture all the images from the simulation model. Thus, capturing the images from simulation model is called synthetic data generation. How do you capture this synthetic data? We'll talk about that on a later on. Uh, but let me know who are the people who are going to try these environmental conditions change, or I'll say weather conditions change for your competition. Let me know in yes or no before I move forward. Oh, oh wow, good, good. I think if the people who said yes adopt it, I think my webinar work is done, because the ultimate aim is to help you guys with adopting industry tools and industry workflows, which can cut down your time so that you can not only focus on your AeroTHON competition, but you can manage your academics also well. So let's move forward from the simulation, and let me talk about resources that we have. So we talked about 6 degree of freedom model blog, and I'm sorry, guys. So we talked about the simulation models, but you would be quite interested. Where can we learn more about all these resources and everything? So let me show you something exciting. If you'll search aerospace block set, you may get a lot of such capabilities introduction on this page. How can you do your atmospheric flight simulation, spacecraft flight simulation, and flight visualization? Uh, I have shown the for flight visualization, if teams are interested to work with us to create and test their scenario in the for the AeroTHON conditions, especially creating the visual scenario, teams can connect with me and I can help you to develop that scenario with Roadrunner. And for all the teams, we are giving the MATLAB and Simulink licenses for this purpose. So please feel free to connect with me. Also, there is this aerospace design learning resources is available. I'll share the link of this with you guys after through the organizers after this webinar. But if you go to this one, this page, you will find all the learning resources in form of videos, examples of developing all your aircraft and developing flight simulation. Now I know you guys have seen good amount of flight dynamics understanding in the fixed wing aircraft, but you would be more interested to know make it for the how can you make it for the your rotorcrafts. So let me know who wants to learn about rotorcraft dynamics. Just tell me I in the chat. Allow me to change my screen. Can anyone let me know if my screen is visible?
Yes, sir.
Okay, thank you. So when we talk about the dynamics of drone motion, it's nothing crazy. If you have understood well about the fixed wing flight dynamics, it's similar, because although we took a fixed wing example, but this is more an aerospace vehicle. Your rotorcraft is also an uh, aerospace vehicle, whereas your fixed wing aircraft is also an aerospace vehicle, and your spacecraft is also an aerospace vehicle. But if you look at the forces that are acting on a vehicle, which is rotorcraft, you will see that obviously the motors are running, and because of motors, thrust are generated. So thrust is always acting upwards in this case. Uh, Gravity always acts downwards, and gravity's direction doesn't change with the orientation. So thrust is our propulsive force, and weight is over gravitational force. The third force is aerodynamics force, which are the lift and drag. And now when we take the components of thrust, the one component goes as lift and another component goes as the forward motion force. So these two lift and forward motion force are the components of your thrust force. And because of the motion of these vehicle forward, as we know, if we are not working, if we are not in the vacuum, if we are in the actual environment, your vehicle faces drag and drag is acting backward. So that's the simple flight dynamics of your vehicle. So now no major changes we need to do to model your aerospace vehicle in the model your rotorcraft as an in the flight simulation. We need to take care of only the direction of the forces which are acting. And by implementing this, we can do it. But before I go forward, I have a small questions for you guys. Consider I have two configurations of the drones. The one is the A configuration where the rotors are rotating in the same direction. The another one is B is moving in the opposite direction. What do you think? Which configuration will provide stable motion? A or B? Can anyone let me know why? What will happen? What will happen if I go for A? Okay. Can anyone let me know why do we go for B and what will happen if we go for A? Will you in A configuration counterbalance counterbalance the torques? These are not torsion forces, but counterbalance the moments created by both of the vehicles. But I was curious, like, what will happen if I move the both the rotors in the same direction? And we tried, and let's see how does it do. So if it goes, this is a small video I have, and you can see this. This is continuously yoing. It's just lost, and somehow it crashed. So we need to counterbalance the moments which we get from the various motions. So you will see that for the rotorcraft, always the diagonal rotors are rotating in the opposite direction. Uh, with this understanding, I know there is much more about how should we control the rotors, uh, which motor should be going, we should be given the more force, more thrust, we should be given the less throttle. We'll talk about all of these things, but maybe in the next section where we are going to talk about the controls of these drones. So till then, please hold your curiosity here. Now we'll move to the another example and we'll see that how is it implemented for the rotorcraft. But a quick check before we go forward. Do you guys want a 3 minute 3 minute break for stretching, having some water? Maybe we can get back on 6:10. Great. Sounds good. So let's take a quick break. I'm putting a small watch here. Uh, Go grab some water, use washroom, come back. I know we are on the cutoff time, so I'm not keeping the 5 minutes, but let's keep it 3 minute window and quickly come back and discuss more. Okay. Thanks, Manjuri, for letting me know. So, uh, if you guys are back and ready to start, just let me know in the chat you are ready. Just type ready. Suman, can you just mute the people? Okay. I see most of the people are saying they are ready. So before we go forward, move forward, let's go back to our previous slide deck. Let's see, where were we? Okay, now we talked about few things, few good things here, right? We talked about, we started this with the example that how can we develop, how can we do the flight simulation? But let me pose a question to you before we go forward. You saw here we need the we need the all the equations of along with the equation of motion, we need the various information about your aircraft's aerodynamics and your propulsive forces. What at the start of competition in phase one you were and you haven't built your vehicle and you want to test your planning algorithm. Or consider another scenario. You have teams, one team is responsible for doing aerodynamics analysis. Another team is responsible for avionics and taking care of your autonomous part. Will you make your autonomous team, autonomous algorithm development team, wait till your aircraft's data is ready? Aerodynamics team is coming up with data. Are you till will you make it wait? Would it be right approach? No, but we are doing good simulation, right? We are getting the full flight simulation capabilities here. We know we need the aerodynamics data, we know the propulsion data, we should have a good estimate of your vehicle. We also know the inertia of your vehicle because we need to provide all these information. But what if we don't have this information? Any guesses? Okay, would you do it for your team or not? Just tell me yes or no. If your team has to wait as a team lead, what would you do? Okay, so there were a good number of people who were loving the simulation, and I don't see these people are talking now. Looks like everyone is not back from the break. Okay, let me bring this problem in a better way to you. So let's talk about your aircraft design journey. So when you are your early stage designs, you may not have very so many aircraft data, right? When you move to the mid design phase, you may have the some aircraft data, and the late design phase where your complete aircraft is designed and everything is in place. In that late design phase, you may have the all the aircraft dynamics variables and everything is available. But what if you don't have that at current stage? How are you going to start? Can we start? Would it be good advice to start our simulation with few of the parameters? Is it possible? Can we do it? What do you think, guys? Or do we need some tools which can help us for making it easier? Without your interaction, I'm not going to move forward with the next thing. We can get some test data to fill the gaps in the data. Okay, what else? Tell me, what else we can do with this? No idea? Okay, so this philosophy goes with the just, I'm sorry for this glitch here. Ignore this part of infographic. But when we are on the early stage design, we go for something called low fidelity model. So in the low fidelity model, if we go, we have the UAV guidance block, which just takes your controls information, like how you want your UAV to perform, right? What should be your UAV's desired characteristics? What parameters it take? We'll get into this. But first we go for UAV guidance block. This is given in as a part of our UAV toolbox. You can use this, and at very initial level, you give it to your team so that your team can, even if your vehicle is not built, they can work on your autonomous algorithm part. And later on, when you get your aircraft's data, they can come back, they can just bring your plant model here and they can make it work. Moving forward, if you get some data, like you're not very sure if the still the you have all the points, but if you have some information about lift, drag, weight, and thrust, in that case, you can use this one. Just allow me for a second, guys. Uh, So in that case, you can use this UAV point mass block. Don't worry, I'm going to show you their implications also in the Simulink. Here at this phase, you have few of the parameters information, and you can use the UAV point mass block to test your design. Moving forward, when you have all the data, that's where you go for your, this is not UAV point mass block. This should be the 6 degree of freedom block. So let me correct it. So yeah. So with your 6 degree of freedom block, you can do the final simulation. So now we have another model where we can see that how the simulation works and how is it going to bring the various plants. So let me bring this MATLAB window to you. We have this project of low fidelity to high fidelity simulation models. Let me bring all my request site. So we have this low fidelity to transition from low fidelity to high fidelity UV model. I'm pasting the link of this in the chat where you can learn more about it, but let me give you a go through in the Simulink. So as this infographic says that low fidelity model where you have lowest information available, moving forward when you have preliminary aerodynamics information is available along with your motor selection and design specifications, then you go for mid fidelity. Once all your sensors are procured, your sensor are freezed, your controller is freezed, then you can go for this high fidelity modeling. So let me show you like from where did we start and where are we going. But before that, I want you guys to answer me one question. This RC aircraft simulation model that we have, do you think it's an open loop simulation or a closed loop simulation? Let me know. Let me know in comments. Is it an open loop simulation or closed loop flight simulation? It's a closed loop. I think close. How are we closing the loop? How are we closing the loop here? We are feeding the states into the environment model, but that for actually estimating how my what is my aircraft's new state. So consider we started from x naught state and we put a control and we want, then we'll calculate x1. But if we want to calculate x2, my x1 need to be feeded. So this is the basic philosophy of simulation. That's what we saw in the previous slide. But is it a closed loop flight simulation or not? Right now, here we see the pilot input I'm giving, right? I was giving the pilot input, or if I'm not giving the pilot input, still my aircraft is flying is dependent on the some type of pilot input. So now you think, is it an open loop or closed loop? I'm closing the loop, but if there is no human involved, will it be a closed loop simulation? Yes or no? It is necessary for you to understand it because this is going to be the foundation of our next session. where we are going to talk about your flight controller, flight computers, and how do you generate the code for them and how do you deploy that. Exactly, it doesn't have any sensors. Correct, Ishant. It doesn't have any sensors which are giving it information. So moving forward, we'll see that how the closed loop flight simulation comes. But before that, let's gets into this example and see that how the open loop flight simulation works. So I have this low fidelity simulation plant model is available. Let me open this and bring it to you and show it what all information it got. This is a very simplistic model, does not involve so many things here, but we would be able to see the very basic vehicle behavior or the control behavior for an estimated vehicle. And also the idea is to see what parameters it got. So you think, see here, we are getting step control input as an airspeed that we want to control, and we are giving it as an output again, right? Here, the low fidelity model, if we go for what is getting, it's getting the controls input. Let me make it easier to visualize. Can anyone let me know if it is readable for you? Is it readable? Okay, good. So it is taking the control input, and we saw in the control input, we didn't have much parameters, only just the one input we gave that we want to control the airspeed, which has the step control. You can see the step control was, this was our step control. This is we giving in the fixed wing model aircraft. And now the environmental parameters, we are giving what are the wind parameters and what is our gravity parameters we're giving. But let's get into this UAV guidance model. And what does information it take? If you see here, this is taking your initial state. Yes, 6 took it. It's taking the information about configuration. It's taking the input output bus names. So what are our input output bus names are controls and environment bus names. We'll see it here. Now, if I go into this depth of these parameters, initial states you see north position, airspeed, these are fine. These parameters we gave in the 6 as well. But in the 6 degree of freedom high fidelity simulation, what we did, we also tried to bring various forces and moments. And we calculate all the forces and moments. So where are these forces and moments? We are not considering these forces and moments here. This is a very high level reduced order model for a closed loop system, including which includes your UAV dynamics and autopilot. And now if you look for the variables that it considers, it is considering the gains. What is your P height? For your height controller, what is your PID controller's P gain? Similarly, what is your flight path angles P, P gain? Then PD roll angle, for roll angle, what is your PD? So all these parameters are actually need to be mentioned here. So this is actually what you are giving here is, think about, your flight controller's gain. This may be your adequate performance that you want to achieve from your controller, and you are putting it here. And it is a reduced order model. So you don't have the information about your aerodynamics forces, gravity forces, your vehicle mass. But what you are getting is you are going to give its control inputs. Now, when we talk about the closed loop flight control simulations, what happens is from your sensors, all the data of state parameters is collected, and this data is fed to a guidance algorithm. Now, this guidance algorithm develops the desired control command, which is fed to the controller. Here, we are just seeing that only the control parameters it taking. We don't have the sensors, we don't have a guidance, we don't have the information about the plant, but still we would be able to implement over vehicles. Still, we would be able to test our guidance algorithm here. So that's called the low fidelity simulation model. Are there any doubts related to low fidelity simulation model, or should we move to the medium fidelity? Let me know in the chat if you have doubts. I see so many names. Ishant saying no. Ishant is consistent, very consistent with the session. Is consistently answering these sessions. I saw a few of the name Ishan, Adi, Ronak. These few students are really great guys. You're giving good attention. Sorry if I'm missing the names of others because in the chat it's going up and down, but you guys are doing wonderful. Keep learning, keep growing. So yeah, if you guys have no doubts, let's move forward and set up it for medium fidelity plant. So I set it up for medium fidelity plant. Uh, in the slides, we saw that we had this UAV point mass block. Uh, now, the UAV guidance block, what we used in the previous one, it has the both fixed wing and rotorcraft rotorcraft configurations. So although in the simulation, what we saw was the fixed wing configuration model, but let me bring it here. This is fixed wing UAV guidance model we saw in the low fidelity model, but you can always check it, change it to multi-rotor guidance model, and you will see that all the parameters will change. So what is taking world position, configuration, the same parameters. It's taking your mass, your thrust, your rate, PD control parameters, and it's taking your initial state parameters. So don't think it's just for the rotorcraft, fixed wing aircraft, but it is for the rotorcraft you can also use. Let me set it up for the medium fidelity plant and go for. So now you observe here the low fidelity plant model. Let me set it up for medium fidelity plant. And let me simulate this. Exception, the busted. Okay. Just a minute, guys. Looks like there is some error on my end because of not closing few things. Let me reset it. Okay, let me just restart it. Okay, till the time I restart this example and show you again the next things. Let me know, guys, what if you have any doubts, because we have next 30 minutes and we have two more topics to cover. So before we get into the various fidelity models, uh, one questions I have, and let me know. Do you think you need always the photorealistic simulations, what we saw in the high fidelity simulation model, how we had the complete airport scenario? Do you really need it? Or at what stage do you need? So we have photorealistic simulation where you bring the 3D scenario. We saw there was an airport, but for such an airport scenario, do we really need it? Or we don't need an airport scenario? Uh, just a 3D model and ground for reference. In things like disaster management where mistakes can be an option, cannot be option. Simulations must be photorealistic, I guess. True. So when we go for the photorealistic simulation, benefits of it is you can uh, actually click the pictures of the environment and use it for your model development as well. Like you want to train your neural network, or you want to train your image processing system, you want to test it. For all these purposes, we need it. Photorealistic simulation has its own needs, but there can be the time at the early stage when you are not still implementing your guidance algorithm, or you don't have a camera sensor on board. You may be good with some scenario which actually depicts obstacles, maybe just some 3D buildings, which can be some rectangular boxes or some cuboids, or maybe some cylindrical objects, right? For all these purposes, we have the various scenario managers where you can develop the cuboid scenario, or you can develop the 3D realistic scenario, or you can just mention some points as an objects and you can do it. Maybe I can share the resources about this scenario generation later on, because these are not going to be the part of this session. But our major attention is to learn about the fidelity simulation and the flight simulations that all we have. Once we are done with the flight simulation, at the last, we are going to talk about how can we do the synthetic data, how can we generate this synthetic data from the flight models. And I'll also show you a quick example, how does a closed loop flight simulation looks like, but we are not going to run the closed loop flight simulation in detail because flight controller, flight computer, it is the subject of our next session. So it's taking time, but in the meantime, let me check if we can go to the slides. Okay, the next topic is a multi-body drone simulation. Good enough. So yeah, let's wait. So we are ready. System is showing we are ready. Good. Set up plant. And to set up, simulate the plant. This is my medium fidelity plant model is there. This because I have restarted MATLAB. Whenever we restart, it takes some time, but no worries, it will give us results. Okay. No more technical questions at this point, but can you let me know in the chat which university or which institutions are you coming from? I want to understand where all we could reach. Maybe your university name and the city, if you can let me know in the chat. Which university you guys are? I have seen there was someone from UIET Punjab, KLE Tech, NIT Uttarakhand. Oh, I'm already working with you guys. Pune, DY Patil. Oh, yeah. Thanks, Ravish. Am I audible, guys? PVG, COET, Pune. Really good. Okay. So I'm seeing continuously some plots are coming up as results. CUSAT. CUSAT. Where is it located, guys? If you can let me know the city, that would be great. So this simulation model is running, and continuously I'm getting these curves generated. These curves are nothing but our visualizations, and these visualizations are, as I said, that every time you may not need the photorealistic simulation. Sometimes we just need these curves to understand how a system is behaving. So you can see that for low fidelity response and mid fidelity response, how my system was behaving differently. So low fidelity response is with the orange color dotted one, and medium fidelity is with blue color. So some response we see that it matches, some response it doesn't. And yeah, no, that's how it works. More and more fidelity you get, you will see that there are few parameters you need to fix, there are few parameters you need to involve, and that's how you actually continuously take the feedback from verification and validation and update your system, optimize your system. So these are the results we got, but let's guess we are more interested into the getting into this model, that plant model what we have. So now if we go into the UAV dynamics plant model, what do we see here is vehicle dynamics, and vehicle dynamics we see here there is fixed wing UAV point mass model is there. So let's get into the point mass model. It's taking all your initial cross range, down range, altitude, initial airspeed. It's taking all of these parameters. Uh, These are the similar to the 6 degree of freedom model, but one thing to notice here is it is taking directly the forces lift, drag, but it's directly taking the forces lift, drag, weight, thrust. Earlier in the last model where we were working, we had all of this lift, drag, weight, thrust were we were computing separately, and then we were feeding them as an total forces and moments. But fixed wing point, UV point mass, when we don't have the complete information, if these basic information is available, still we can make it work. So let's get into the calculate forces and see that how detailed it is. So we are seeing that even the wind is calculated within here. We are seeing the roll dynamics is calculated here. For aerodynamics, they are just calculating lift, drag, and thrust. No other detailed information. And that's the level of simplicity, low fidelity modeling, and medium fidelity simulation brings. We started with high fidelity simulation modeling to understand what all do we need. But as we start our design process, we may not have all the design parameters, but sooner we start gathering all the design parameters, all the aerodynamics parameters, your mass parameter, your propulsive parameters, and that's how you bring them together and bring your flight vehicle closer and closer to the your realistic condition. So let's go for this final high fidelity plant model before I show you how do you do the synthetic data generation. So let's go for the simulate plant model. We are setting up this high fidelity model. So this is this is a project mode in MATLAB where you can create your own shortcuts and you can set your system. So whenever I'm hitting a shortcut, it's at behind it is running a MATLAB file, which is actually setting up all the parameters in such a way that it select your low fidelity model, medium fidelity model, or high fidelity model. And at last, I'm going to show you is like this, all these model, low fidelity, medium fidelity, high fidelity model, or everything is in only one Simulink model. It's not that I have 3 Simulink models I'm creating and I'm running it. So think about everything just at one place, and we are working, we are just working on the uh, we are working on the one model. So it should start. Let me close the or previous results so that we can see the new results. Okay, good. We have these results started popping up. Okay. One quick question, guys. What do you think at this stage, if your team start working, at what level your team is going to work? Is it work, you are going to work on low fidelity model, you're going to work on medium fidelity model, high fidelity model? What is your current stage? You guys have just completed phase one. You have done some simulations, CFD simulations, or your thrust bench test. You got these data. How are you going to bring this together and have it? So Ishant is telling you are right now at the medium and high fidelity models. Good. Any other team? Ishant, from which institution you are? Let me just drag and drop this one. So again, we can see that how our response was for medium fidelity model, which is in the dotted blue line, and this more like a red line we have is going to be for the high fidelity simulation, and we see this, how the variation is coming. Ishant is from NIT Uttarakhand, thank you. So we see that as we bring more and higher fidelity models, we see that the controller we designed, how is it performing with our vehicle? So there is always an area of improvement that you do, and you bring your flight vehicle close to this. Even when your high fidelity simulations are done and you fly the vehicle, you may find that due to manufacturing deficiencies or due to manufacturing or data acquisition changes, or maybe to environmental factors, your performance may change. So there is another option to capture all these data, flight data from your vehicle, and comparing your simulation model and flight model. So if any team is interested to work with us on this, please feel free to directly reach out to me on the LinkedIn or the roboticsarena@mathworks.com. I'll put that email ID here. So yeah, you can see all of these simulation models can, but now let's get into the Simulink model and see that what is in the high fidelity model. So in the high fidelity model, you see I have this plant model, which is getting UV dynamics. Okay, you see this, all the forces and moments were calculated, and forces and moments are fed to the 6 degree of freedom equations of motion. That's where we started learning that how does the 6 degree of freedom model works. But along with the 6 degree of freedom model and forces and equations you see here, it has the weather model, it has also the GPS and state data, so it has some sensors as well. So using all of these scenarios, using all of these parameters, you actually navigate from low fidelity modeling to high fidelity simulation, how high fidelity modeling, and you perform the simulations. So now that's how you all do. Uh, I know we are close on the time, but let me show you another exciting things. So are you guys interested to see the package delivery example that we have? Are you excited to see how does a drone goes into a US urban environment and deliver an UAV from one location to another? Looks like all the students has learned that I'm not going moving forward without their yes. Oh, great, guys. So when you guys are working for your models for AeroTHON, and if you guys face any issues, always feel free to connect with me on these models. And just a minute, guys. I'm putting I'm putting the email ID here where you can always reach out to me, reach out to our team. So this is the roboticsarena@mathworks.com email ID, where the team of dedicated engineers can help you with your queries. You can always reach out to me on LinkedIn. Few of the teams are already connected with me, and I'm happy to help other teams also who are willing to work forward with me and make an impact make an impact with industry workflow. Tomorrow, you guys are going to be in industry. Your academics are going to be over soon, but tomorrow when you go for the industry demands model-based design workflows. And if you learn these workflows, you have the edge over your peers. That will help you to get better prospect, maybe in research, maybe in corporate, wherever you go. So let's move back and see this package delivery example. But yeah, last things first, let's run the model and see this. How does it look like? Because now I'm no more into the teaching mode, but I'm into the excitement mode. That how does it work? Let's work, guys. Come back. Okay, am I audible, guys? Am I audible? Okay, fine. So this model simulation is working, is actually running now. But if you see this is actually called the closed loop flight simulation model, where we say that there is a multi-rotor plant model is there, which has the onboard computer. It can be a Raspberry Pi or NVIDIA Jetson, where you put your flight computer algorithm. It can have also flight controller PX4 autopilot. We'll talk about it. How does it work? But let's see this. For this simulation, you see my UAV started running and going there. Let me rerun it to show you how is it working. So this is working in a low fidelity model now. So you will see the very simplistic setup. The rotorcraft came in, it took off and moved into this environment. But let me show you this in actually the form we want to set. So this example is a package delivery example where you can actually set up a cuboid scenario as well. You can set up obstacle avoidance algorithm, photorealistic simulation. So I'm going to connect it with my ground control station. So most of you would have heard about Q ground control and mission planner. So what is a Q ground control and mission planner? These are nothing but your ground control stations. So using this ground control station, we can always make our vehicle run in the simulated environment. Okay. And let me set it to the photorealistic simulation first. And let me fly this plant. Let me fly the full mission here. Where is my Simulink model? Okay, Simulink model is available here. Now, my ground control station is also ready. Let me open the storage. Missions. Why don't I see any missions here? No worries. Let me get the mission file. So this my mission plan is there that I'm going to put up on my vehicle and I'll try to fly it. So let me set up the QGC also along with it.
All right.
So my ground control vehicle, you can see that it got armed here. You can see here, my vehicle is armed, and let me bring the simulated vehicle here. So this is my simulated vehicle is also coming in the scenario. Now it's time to run this. Okay, this is starting and we can see that this is actually running through the simulation. Here a camera sensor is actually modeled here, which is gathering all the images that our rotorcraft is seeing, and we are seeing that here my vehicle is following, and you can also see here the vehicle is moving. My flight path didn't get uploaded, so we do not see the uh, exact point-to-point performance, but yeah, if I rerun it, it will work it. How to connect QGC with MATLAB? Okay, so Vinay, we have a script with QGC with MATLAB. So this is done via the UDP communication. So in MATLAB, we have Simulink, we do have the UDP PDP communication protocol blocks which are used. Don't worry about it. In the next webinar, next session, when we are talking about it, we will talk in detail about all these things. And you can learn in detail like how how do you bring various IP addresses, how do you connect it to remote vehicle, how the Mavlink works, how the USB communication works. We are going to talk about it. But yes, please keep your questions ready. And if you want to try these workflows in the next session, just reach out to me on the robotics arena at mathworks.com and you'll see that how the vehicle is going. Now you can see that this QGC, in the QGC, my ground control station, my vehicle is continuously moving and it has taken a turn as well, right? And that's how you can plan your mission with QGC and implement it using Simulink and do the photorealistic visualization. You can get the pictures here from your camera, and from camera you collect all these pictures and feed it for your neural network or your image processing or your computer vision system training. Does it sound exciting, guys? Does it sound something which would be useful for you? Yes or no, guys? Oh, really, really, really good to know. Really good to know. It's interesting. See, uh, the workflow that we have in the simulation, you can see that how do we start? We bring the flight dynamics modeling. We talked about 6 degrees of freedom modeling, and then we go for, hey, let's think about, we don't have all the parameters of aerodynamics and propulsion already. Can we still work it? So we went for low fidelity modeling, medium fidelity modeling, and we also talked about the high fidelity modeling with this one. And we see this environment is ready, or drone is actually getting launched, and it launched from there, it took off, and now it's getting landed. So your complete autonomous mission part that you want to do, you can do it. I forget to bring this picture, but here a LiDAR was also connected, which was actually giving all the information. So that's how you can bring this. Now my vehicle has landed, and so you see this here, where we saw the arm, now it shows the communication lost because my Simulink has stopped the simulation. And that's, you can see that this stopped, and that's how our simulation works. Isn't it quite interesting, guys? Okay. Now I'll not get into the details. You can see there is a cuboid scenario. Method is also available, but we are on the crunch of time. So we will not get into it, but I'll show you another demo, which I had, which we have shared during the AeroTHON last year. And there was one team, Bits Pelani Goa team, which used this synthetic data, generated synthetic data from this example, from this demo, and they retrained the model during the competition. And this team actually won one of the autonomous award competitions, or autonomous awards for this. So let me just bring the demo that we have. Last event is bad, my bad. Okay, so now we are not going into bringing so many fancy things. We talked about synthetic data simulation. Sorry, we talked about flight simulations. Now the idea is to bring it in a very simple way. So what we did is this, think about your flight simulation is ready, and somehow you are getting your position and altitude. We talked about simulation 3D scene configuration environment. So you have a simulation 3D scene configuration environment from where you can bring. So you can see that here in the Roadrunner, we have created a scenario for the aerospace for AeroTHON 2024 event, right? So this is a synthetic scenario we created, and we put it here, and we bring this simulation 3D camera. Before we get for simulation 3D camera, see this. This is UAV vehicle, and in the UAV vehicle, if you see this, it's a type is quad rotor and color is black, but focus on this name, right? Let me focus it back. Its name is Simulink Vehicle 1. Please note it. Now, if I have the name of the Simulink vehicle which we want to, I'll bring the simulation 3D camera from your computer vision toolbox here, and I can actually put the camera on it. You see this. Where is it mounted? It's mounted on the Simulink Vehicle 1. Parent name Simulink Vehicle 1. Compared to CG, what is relative location? So you see this relative location we have put up as the translation XYZ relative rotation role pitch you put it, and that's how you set up your camera. Now let me do it in a very simplistic way. Let's run this model. This is not be a very crazy model. We have just done a simple thing that on the simulation, we have set up a camera, and it has a video viewer as well, right? Okay, now you see this. That's what my camera is seeing because this is above this, and it has a mathfux logo, which is actually coming inverted. Maybe it's put as inverted, but I see my drone is not moving. So let me change some parameters and redo it. From the simulation 3D camera, we are getting a video viewer and image simulation OP1. So we know this simulation already, there are some videos are already available in the viewer. So I want you guys to give me a specific name in the chat. It may be your team name or anything you want me to name this recording. So team, any team, whoever is going to give me the first name, I'm going to choose their name for this one. Or let's make it third name, which is, okay, Aero KLE, Aeroha. So I'm putting the Aero KLE. .mp4, right? AeroKLE.mp4. This file we are going to get, and in the position and altitude, I'm going to put this as the position was fixed, but now let me put it as in a circle. And this is synthetic data generation model. Let's run it, and let's see how does the performance comes up. So that's my simulation. 3D camera came first, and where you can see this, my vehicle is continuously moving. Okay, now we see this, there is no movement here, but we are seeing this is moving. So there is some issue. Let's correct that issue. What is it? Quickly. So what's happening here is the simulation 3D scene configuration. If I go and I see the scene view, I have put up as scene origin, right? Scene view as scene origin. And that's what creating mistake. So let me change it to the Simulink vehicle 1, and then let's me go for it. My drone is flying in on some location. I can change the views from this, but I'm seeing now it's moving around a circle and it's actually trying to get the pictures, right? That's how it simply works and create the videos. So we have taken some parameters for considering these videos. You can play with these parameters, but let me now quickly show you how this video is saved and how can you convert this video into images. Because when then the third session, when Shovik is going to see you to pre-process the data and use your image data for your model training, this synthetic data will be useful. A combination of synthetic data and actual flight data that you capture will make a very good mix to train the data, and you will see superb results with these data. So you don't need to worry about, hey, this time they have introduced some new object and we don't have the data for it. How are we going to fly this? You don't need to worry about it because all these can be done. So this stop time is infinity. So let me stop it because it will keep running. But now let's go here and let's see if we do have AeroKeli MP4. And that's what we see here. Do you see AeroKeli MP4? Let me just run it outside the MATLAB and show you. Yeah, I did some investigation. And found out that she's not using the standard MP4. Right, that's what we want. So now do you think, can you capture the data for your simulation, for your AeroTHON competition and make it? Yes or no, guys? Now I'll quickly show you how can you convert it into images. So we have created, there is a simple live script is there. So I'm not getting into the detail, how do you set it up and everything, but new directly, let me put it as images, arrow KLE 1. And okay, let me do another thing. So let me take the name of Aroha, right? Aroha has mentioned here the name. So let me put her name as images, Aroha. This I'm going to set up. This will create a directory. Now the simulation video, I have the AeroKeli MP4. So let me just copy paste its name so that doesn't make any issues. For select video file, why I'm doing all the efforts. So we come here, we come here, we come here. Simulation OP. So I see AeroKeli. Let me take it. And this with this AeroKeli file, let me run this, create image sequence. So this is just to change your images into your files and create all the images. So you will see this, once this run, we'll have the all the images ready. So this is running, but in the meantime, let me check where is our folder. Images are getting here. Images arrow, you see this. The number of images, we all have already generated over 2000 images. Sorry, more than that. So that's how you can do the synthetic data generation. I hope you guys liked about the synthetic data generation. Let me know if you guys have any doubt about these demos. Okay, now let me quickly move forward. We are over the time, but I'll give you just a glimpse of the last model that you guys can try. But you guys can try. And if you guys have any question, please feel free to reach out to me. So there's something called multi-body drone simulation in the MATLAB, and we have this specific example where you can simulate a quadcopter flight with physical modeling approach. So by the time whatever we did, 6-stop modeling, and high fidelity, low fidelity modeling, this is all mathematical approach. This is mathematical modeling approach, and this is not a physical modeling approach. So what's physical modeling approach is in physical modeling, you bring various parts together, part by part, all of your CAD geometries, what you see here in your vehicle, that's how you bring them together, fix their constants, how they are connected. Are there a revolute joint or is it a fixed joint? It has some degree of freedom or not. Using this, you do, and you actually uh, get the simulation something like this, where you can see that your quadcopter is actually flying, and you will see that this vehicle will actually go over a mission in the same way you do it, and you can actually drop your payload. So if you want to test your uh, dropping mechanism capabilities along with this, then you can use for the multi-body simulation capabilities. So within the Simulink, we have Simscape. So Simscape multi-body helps you to do such multi-body simulations. It can help you to define your requirements, discover your integration issues, and work with the design control algorithms. So try this, check out this example. Please feel free to reach out to me if you guys have any doubt. Now, we are at the last section of this. I know we had a long workshop. Uh, you have seen that we have multiple demos in MATLAB and Simulink, but you guys would be interested, how can we get the MATLAB and Simulink if we don't have access? So as part of our support to the AeroTHON, we are sponsoring the license for all AeroTHON teams. So you can come to this link and actually apply for your MATLAB and Simulink licenses. Uh, all the teams will get the license for this. I am posting the link of this in your chat. Along with this learning resources, we do have a lot of videos, Central entries. So you can check these entries and work with this. Also, if you guys have uh, not completed your on-ramps on MATLAB and Simulink, that's going to be your first step towards your MATLAB and Simulink journey. And then there are some advanced content is available, which you can easily find it out on this page, where you are going to apply for your MATLAB and Simulink where license. So here you apply for a complimentary software license, and then you see that it has a lot of competition resources, videos, file exchange entries, everything is available here. Also, I would suggest you guys to check out this another page that is the UAV learning resources for students. So if you'll go to on this page, I'm pasting the link of this as well in the chat. You can see that it has the various sections. These sections are divided into beginner, intermediate, and advanced, and it covers the topics like modeling and simulation, flight data access and analysis. How can you gather the flight data and analyze in MATLAB? How do you develop the algorithm development, implementation with ROS, autopilot hardware and software deployment. Today we saw the simulation with the MATLAB only, but if you are interested to do even with the gazebo, there are examples and videos are available. You can check that out. So you can check this example, perform co-simulation between Simulink and gazebo. So you are actually creating all the dynamics modeling in the Simulink and using the gazebo as your simulator. That all you can do. Check out these examples, algorithm examples, videos, and learn about the UVs with MATLAB and Simulink. And please feel free to reach out to me in case if you have any issues. And also check out this MATLAB student tutorial repositories where we have more than 70 videos now, and these goes across the variety of aerospace, robotics, code generation, automotives, and everything. Yeah, and with this, we come with the end of the webinar. But yeah, remember there are MATLAB and Simulink are tools are available. You can use MATLAB and Simulink when you know already the system equations and you need a bigger scientific calculator to solve your equation and process the results. Use the aerospace block set and UAV toolbox to model, simulate, and analyze your flight vehicles for guidance, navigation, and control algorithms. Use Simscape when you need to work on the mechanisms or you need to do the multi-body simulations. So yeah, all these tools are available and all these are part of MATLAB. So you don't need to take it all these, but when you're installing your MATLAB and Simulink, you need to get the access for these. With these, we come to the end of the session and I'm open to the questions, guys. Please feel free to turn on your mic and ask me questions. Any questions related to flight dynamics modeling, various fidelity modeling, the flight visualization, or the multi-body simulation, or synthetic data generation model we have. Abhishek, Ishant, Adi, Ashish, if you guys have any questions, or you can also let me know in the next session what would you like to learn.
Sir, actually, I had a question.
Yeah, yes, Ishant.
Sir, it's pretty basic questions. How
Ishant,
exactly
you
are
are
we
not
designing the
clearly audible.
environment?
You are not clearly audible. Can you come closer to the mic, please?
So can I just type?
Yeah, please feel free to. In the meantime, if anyone else wants to turn on their mic and ask the questions, please. As you said, there are resources available on MATLAB for the task that we can do in Simulink regarding SA AeroTHON competition. Other than what we can refer. Okay, so I have I have put up the link for the UAV learning resources for MATLAB and Simulink. So you can check this page. This is the learning path where you will get everything step by step. Whatever the aspect of UAVs you are going to work, either is modeling and simulation, you'll find a drone simulation and control series completely. So you can learn about how do you develop your flight controller and how do you do the flight simulation. And there is specifically video on the simulating delivery drones in Simscape. So this video you can check out where my colleague Sam Hunt has discussed in detail that how do you bring this complete one and how do you do the package delivery with this one. So I have, although not I'm not clear covering this video, and I have not covered this demo in this one because this video is directly available. Please feel free to go through this and learn. Moving forward, if you are doing the flight data access or analysis, there is another section for developing your autonomous algorithm that may include your uh, uh, computer vision algorithm or your deep learning algorithm. So how do you do the autonomous navigation, sensor fusion, motion planning, uh, making robotics and vehicle seats more like computer vision algorithm, perception for UAVs, all these are available here. And finally, if you are working with ROS, you can go for it, but my personal understanding is you can do it without ROS for AeroTHON. You do not need to complicate it with ROS. And finally, where you are going to implement, especially for your PX4 or Raspberry Pi, if you need it. So there is these code generation capabilities are available, and you can actually explore this UV code development with Simulink webinar, which has the detailed video. But in the next webinar, I'll be talking in detail about that. So you can check there as well. I hope, Om, I could answer your question. If there is anything else, let me know. Okay, Ishant is asking, sir, where exactly do we design environment setup for visualization? Which type of file we use for it? Okay, that's a good question. Okay, let me go for the synthetic data generation model. So think about our flight dynamics model is ready. I'm not going anywhere. So there are two types of environmental model we talked about. One is environment model, which gets included into your flight dynamics. But all the UAV state parameters that our UAV is flying at X speed or say Z altitude or maybe at the P roll and YEO, whatever is its motion, we need to visualize them. And for this purpose, we need to use the visualization model. Now, visualization subsystem where we have to set up the 3D scene where we are actually visualizing this complete scenario scene. So for this purpose, we use the simulation 3D scene configuration. And you can go for this. Now, if you look for this, okay. So this is my scene where I have set up the Roadrunner custom scene. You have seen a MATLAB scene into this. Let me make it, instead of row, let me make a default scene of US city and show you. So this is my US city block. I'm going to run this. Previously, we saw that custom AeroTHON scene. But before I go for that, let's see this. This is a Roadrunner scene, but if you're working with Unreal Engine, you can bring Unreal Engine as files as well. With Roadrunner, if you're working, you have to bring the FBX file, right? So let me just highlight this. You can bring the FBX file here, and with FBX file import, your complete 3D scene would be imported. So I have created this 3D scene. Creating 3D scene doesn't make time. It's as easy as doing a CAD geometry for your vehicle components. So you can bring this. Now, when we do the scene setup, after this, if you want to put up the weather and environment, the idea here is in this one, when you include the weather condition, these weather conditions are not for the creating an obstacle for your flight vehicle. These are just for the visualization purpose. So you can see here we have the uh, sun azimuth attitude, clouds condition, rain, fog, all these are, but these are more for visualization only. If you want to get included into this, then you have to model them into the environment modeling. I hope environment modeling in the flight dynamics. That's what we need to do. So I hope I could answer your question, Nishan. Okay, okay, thanks. Is there any other question, guys? Okay, no queries from Ashish. Okay, what topics would you like to learn in the next session? I know we have a set agenda. I know we talked about it, but specifically, if I would have asked your interest, what is the few topics that you want to learn, so that I make sure that if it is already not covered in the topic, I bring them here and we cover these topics. So this is the US city scene I'm going to run. Hope I have put up the US city scene again there, or let me just recall it. Okay, Roadrunner. Let me cancel the Roadrunner. Bring default scene, which is US city block, and let me run this scene. Okay, so in the next session, we are going to talk about how do you do the code generation from Simulink models. You saw today that we had the various Simulink model. In the Simulink model, we have the guidance controls. So how do you bring these together and how do you create all these scenarios? That's what we are going to talk about. And we'll also talk about how do you deploy the code to Raspberry Pi and Jetson GPUs. That is going to be the topics of our next session. But you can see this is a very well-built USC in city block environment where we are gathering the data using this. And that's what we tried to, we tried that at starting of the webinar the three at the starting of webinar, this was our goal to get into that. How can we create the simulations like this? So these are going to be the simulations. So how do you do the implement avoid obstacle avoidance and algorithm? We are going to talk in the next webinar, but let me know if we could succeed in the goal of today's webinar to learn how can you develop the simulations for AeroTHON, especially the flight simulations. Let me know if we succeed or not. Okay. Uh, Ishant Ronak is saying yes. So Ishant and Ronak, now remember, I'm also in the jury panel of the competition, and I expect you guys to implement this in the AeroTHON. If you guys have any doubts, please feel free to reach out to me. We are always there to support you and help you with these workflows. Please feel free to connect with us, write to your queries. We have a dedicated team of engineers who actually supports the competitions. Thanks a lot, guys. That's all I have for the today. If there is anything else, you can let me know. Thanks, Suman.
Yes, sir.
Suman, can we stop recording?
Yeah, sure, sir.
Yeah, thank you.